Introduction: The historical development of tunnel building. A tunnel, defined as an engineering structure, is an artificial gallery, passage, or roadway beneath the ground, under the bed of a stream, or through a hill or mountain. The art of tunneling has been known to man since very ancient times. A Theban king, on ascending the throne, began at once to drive the long, narrow passage, or tunnel, leading to the inner chamber of sepulchre of the rock-cut tomb, which was to form his final resting place. Some of these rock-cut galleries of the ancient Egypt kings were over 750 feet long. Similar rock-cut tunneling work was performed by the Nubians and Indians in building their temples, by the Aztecs in America, and in fact, by most of the ancient civilized peoples. The first built-up tunnels, of which there are any existing records, were those constructed by the Assyrians. The vaulted drain or passage under the southeast palace of Nimrud, built by Shalmaneser II in 1860 to 1824 BC, is in all essentials a true soft ground tunnel with a masonry lining. A much better example, however, is the tunnel under the Euphrates River, which may quite accurately be claimed as the first submarine tunnel of which there exists any record. It was, however, built under the dry bed of the river, the waters of which were temporarily diverted, and then turned back into their normal channel after the tunnel work was completed, thus making it a true submarine tunnel only when finished. The Euphrates River Tunnel was built through soft ground and was lined with brick masonry, having interior dimensions of 12 feet in width and 15 feet in height. Only hand labour was employed by these ancient people in their tunnel work. In soft ground, the tools used were the pick and shovels or scoops. For rock work, they possessed a greater range of appliances. Research has shown that among the Egyptians, by whom the art of quarrying was highly developed, use was made of tube drills and saws provided with cutting edges of corundum or other hard, gritty material. The usual tools for work here, however, the hammer, the chisel and wedges, and excellence and magnitude of the works accomplished by these limited appliances attest the unlimited time and labour which must have been available for their accomplishment. The Romans should doubtless rank as the greatest tunnel builders of antiquity, in the number, magnitude, and useful character of their works, and in their improvements which they devised in the methods of tunnel building. They introduced fire as an agent for hastening the breaking down of the rock, and also developed the familiar principle of prosecuting the work at several points at once by means of shafts. In their use of fire, the Romans simply took practical advantage of the familiar fact that when a heated rock is suddenly cooled, it cracks and breaks so that its excavation becomes comparatively easy. Their method of operation was simply to build large fires in front of the rock and then to have it broken down, and when it had reached a high temperature to cool, it suddenly by throwing water upon the hot surface. The Romans were also aware that vinegar affected calcareous rock, and in excavating tunnels through this material, it was a common practice with them to substitute vinegar for water as the cooling agent. and thus to attack the rock both chemically and mechanically. It is hardly necessary to say that this method of excavation was very severe on the workmen because of the heat and foul gases generated. This was, however, a matter of small concern to the builders, since the work was usually performed by slaves and prisoners of war who perished by thousands. To be sentenced to labour on Roman tunnel works was thus one of the severest penalties to which a slave or prisoner could be condemned. They were places of suffering and death, as are today the Spanish mercury mines. Besides their use of fire as an excavating agent, the Romans possessed a very perfect knowledge of the use of vertical shafts in order to prosecute the excavation at several different points simultaneously. Pliny is authority for the statement that in the excavation of the tunnel for the drainage of Lake Ficino, 40 shafts and a number of inclined galleries was sunk along its length of 3.5 miles, some of the shafts being 400 feet in depth. The spoil was hoisted out of these shafts in copper pails of about 10 gallons capacity by windlasses. The Roman tunnels were designed for public utility. Among those which are most notable in this respect, as well as for being fine examples of tunnel work, may be mentioned the numerous conduits driven through the calcareous rock between Subiaco and Tivoli to carry to Rome the pure water from the mountains of Subiaco. The work was done under the consul Marcus. The longest of the Roman tunnels is the one built to drain Lake Ficino, as mentioned above. This tunnel was designed to have a section of 6 foot times 10 foot, but its actual dimensions are not uniform. It was driven through calcareous rock, and it is stated that 30,000 men were employed for 11 years in its construction. The tunnels which have been mentioned, being designed for conduits, were of small section, but the Romans also built tunnels of larger sections at numerous points along their magnificent roads. One of the most notable of these is that which gives the road between Naples and Puzzoli passage through the Posillipo hills. It is excavated through volcanic tufa and is about 3,000 feet long and 25 feet wide, with a section of the form of a pointed arch. In order to facilitate the illumination of this tunnel, its floor and roof were made gradually converging from the ends towards the middle. At the entrances, the section was 75 feet high, while at the center it was only 22 feet high. This double funnel-like construction caused the rays of light entering the tunnel to concentrate as they approached the center, and thus to improve the natural illumination. The tunnel is on a grade. It was probably excavated during the time of Augustus, although some authorities place its construction at an earlier date. During the Middle Ages, the art of tunnel building was practiced for military purposes, but seldom for the public need and comfort. Mention is made of the fact that in 1450, Anne of Lusignan commenced the construction of a road tunnel under the Col de Tenda of the Piedmont Alps to afford better communication between Nice and Genoa, but on account of its many difficulties, the work was never completed, although it was several times abandoned and resumed. For the most part, therefore, the tunnel work of the Middle Ages was intended for the purposes and necessities of war. Every castle had its private underground passage from the central tower or keep to some distant, concealed place to permit the escape of the family and its retainers in case of the victory of the enemy, and during the defence to allow of sorties and the entrance of supplies. The tunnel builders of the Middle Ages added little to the knowledge of their art. Indeed, until the 17th century and the invention of gunpowder, no practical improvement was made in the tunnel methods of the Romans. Engravings of mining operations in that century show that underground excavation was accomplished by the pick or the hammer and chisel, and that wood fires were lighted at the ends of the headings to split and soften the rocks in advance. Although gunpowder had been previously employed in mining, the first important use of it in a tunnel work was at Malpas, France, in 1679 to 81, in the tunnel for the Languedoc Canal. This tunnel was 510 feet long, 22 feet wide, and 29 feet high, and was excavated through tufa. It was left unlined for 7 years, and then was lined with masonry. With the advent of gunpowder and canal building, the first strong impetus was given to tunnel building in its modern sense as a commercial and public utilitarian construction since the days of the Roman Empire. Canal tunnels of notable size were excavated in France and England during the last half of the 17th century. These were all rock or hard ground tunnels. Indeed, previous to 1800, the soft ground tunnel was beyond the courage of engineer, except in sections of such small size that the work better deserves to be called a drift or heading than a tunnel. In 1803, however, a tunnel 24 feet wide was excavated through soft soil for the Saint-Quentin Canal in France. Timbering or strutting was employed to support the walls and roof of the excavation as fast as the earth was removed, and the masonry lining was built closely following it. From the experience gained in this tunnel were developed the various systems of soft ground subterranean tunneling since employed. It was by the development of the steam railway, however, that the art of tunneling was to be brought into its present prominence. In 1820 to 26, 2 tunnels were built on the Liverpool and Manchester Railway in England. This was the beginning of the rapid development which had made the tunnel one of the most familiar of engineering structures. The first railway tunnel in the United States was built on the Allegheny and Portage R&R in Pennsylvania in 1831 to 33, and the first canal tunnel had been completed about 13 years previously, 1881 to 21, by the Schuylkill Navigation Company near Auburn. It would be interesting and instructive in many respects to follow the rise and progress of tunnel construction in detail since the construction of these earlier examples, but all that may be said here is that it was identical with that of the railway. The art of tunnelling entered its last and greatest phase with the construction of Mont Cenis Tunnel in Europe and the Hoosac Tunnel in America, which works established the utility of machine rock drills and high explosives. The Mont Cenis Tunnel was built to facilitate railway communication between Italy and France, or more properly between Piedmont and Savoy, the 2 parts of the kingdom of Victor Emmanuel II, separated by the Alps. It is 7.6 miles long and passes under the Col de Frigide near Mont-Cenis. Sommelier-Gratoni and Grandis were the engineers of this great undertaking, which was begun in 1857 and finished in 1872. It was from the close study of the various difficulties, the great length of the tunnel, and the desire of the engineers to finish it quickly, that all the different improvements were developed which marked this work as a notable step in the advance of the art of tunneling. Thus the first power drill ever used in tunnel work was devised by Sommelier. In addition, compressed air as a motive power for drills, aspirators to suck the foul air from excavation, air compressors, turbines, etc., found at Mont-Cenis their first application to tunnel construction. This important role played by Mont-Cenis Tunnel in Europe in introducing modern methods had its counterpart in America in the 𝐥𝐤𝐤𝐞 Tunnel completed in 1875. In this work there were drills for the first time in America, power rock drills, air compressors, nitroglycerin, electricity for firing blasts, etc. There remains now to be noted only the final development in the art of soft-ground submarine tunneling, namely the use of the shield and metal lining. The shield was invented and first used by Sir Isambard Brunel in excavating the tunnel under the River Thames at London, which was begun in 1825 and finished in 1841. In 1869, Peter William Barlow used an iron lining in connection with a shield in driving the second tunnel under the Thames at London. From these inventions has grown up one of the most notable systems of tunneling now practiced, which is commonly known as the shield system. In closing this brief review of the development of modern methods of tunneling, to the presentation of which the remainder of this book is devoted, mention should be made of a form of motive power which promises many opportunities for development in tunnel construction. Electricity has long been employed for blasting and illuminating purposes in tunnel work. It remains to be extended to other uses, for hauling and for operating certain classes of hoisting and excavating machinery. It is one of the most convenient forms of power available to the engineer. Its successful application to rock drills is another promising field. For operating ventilating fans, it promises unusual usefulness. When a railway line is to be carried across a range of mountains or hills, the first question which arises is whether it is better to construct a tunnel or to make such a detour as will enable the obstruction to be passed with ordinary surface construction. The answer to this question depends upon the comparative cost of construction and maintenance, and upon the relative commercial and structural advantages and disadvantages of the two methods. In favour of the open road, there are its smaller cost and the decreased time required in its construction. These mean that less capital will be required, and that the road will sooner be able to earn something for its builders. Against the open road there are its greater length and consequently its heavier running expenses, the greater amount of rolling stock required to operate it, the heavy expense of maintaining a mountain road, and the necessity of employing larger locomotives with the increased expenses which they entail. In favour of the tunnel there are the shortening of the road, with the consequent decrease in the operating expenses and amount of rolling stock required, the smaller cost of maintenance, owing to the protection of the track from snow and rain, and other natural influences causing deterioration, and the decreased cost of hauling due to the lighter grades. Against the tunnel there are its enormous cost as compared with an open road and the great length of time required to construct it. To determine in any particular case whether a tunnel or an open road is best requires a careful integration of all the factors mentioned. It may be asserted in a general way, however, that the enormous advance made in the art of tunnel building has done much to lessen the strength of the principal objections to tunnels, namely their great cost and the length of time required for their construction. Where the choice lies between a tunnel or a long detour, with heavy grades it is sooner or later almost always decided in favour of a tunnel. When, however, the conditions are such that the choice lies between a tunnel or a heavy open cut with the same grades, the problem is deciding between the two solutions is a more difficult one. It is generally assumed that when the cut required will have a vertical depth exceeding 60 feet, it is less expensive to build a tunnel unless the excavated material is needed for a nearby embankment or fill. This rule is not absolute, but varies according to local conditions. For instance, in materials of rigid and unyielding character such as rock, the practical limit to the depth of a cut goes far beyond that point at which a tunnel would be more economical according to the above rule. In soils of a yielding character, on the other hand, the very flat slope requiring for stability adds greatly to the cost of making a cut. It may be noted in closing that the same rule may be employed in determining the location of the ends of the tunnel, for assuming that it is more convenient to excavate a tunnel than an open cut when the depth exceeds 60 feet. Then the open cut approaches should be extended into the mountain or hillsides only to the points where the surface is 60 foot above the grade, and there the tunnel should begin. If, therefore, we draw on the longitudinal profile of the tunnel a line parallel to the plane of the tracks and 60 foot above it, this line will cut the surface at the points where the open cut approaches should cease and the tunnel begin. This is a rule of thumb determination at the best, and requires judgment in its use. Should the ground surface, for example, rise only a few feet above the 60-foot line for any distance, it is obviously better to continue the open cut than to the tunnel. When it has been decided to build a tunnel, the first duty of the engineer is to make an accurate geological survey of the locality. From this survey, the material penetrated, the form of section, and kind of strutting to be used, the best form of lining to be adopted, the cost of excavation, and various other facts are to be deduced. In small tunnels, the geological knowledge of the engineer should enable him to construct a geological map of the locality, or this knowledge may be had, in many cases, by consulting the geological maps issued by the state or general government surveys. When, however, the tunnel is to be of great length, it may be necessary to call in assistance of a professional geologist in order to reconstruct accurately the interior of the mountain, and thereby to ascertain beforehand the different strata and materials to be excavated, thus obtaining the data for calculating both the time and cost of excavating the tunnel. The geological survey should enable the engineer to determine the character of the material and its force of cohesion, the inclination of the different strata, and the presence of water. The character of the material through which the proposed tunnel will penetrate is best ascertained by means of diamond rock drills. These machines bore an annular hole and take away a core for the whole depth of the boring, thus giving a perfect geological section showing the character, succession, and exact thickness of the strata. By making such borings at different points along the center line of the projected tunnel, and comparing the relative sequence and thickness of the different strata shown by the cores, the geological formation of the mountain may be determined quite exactly. Where it is difficult or impractical to make diamond drill borings on account of the depth of the mountain above the tunnel, or because of its inaccessibility, the engineer must resort to other methods of observation. And that concludes tonight's readings. I hope you enjoyed it, and I hope you're feeling drowsy. You're always welcome to listen to another episode, and in the meantime, good night.